about the theorem. So it directly doesn't have many applications in problems, but still there are a few which we shall see. So what are we looking at? We are looking at it for continuous functions. Continuous functions. Okay. So let's do it in a straightforward setup. So f is a function that is continuous from a closed interval. Now here a closed interval is very important. We will try to abstract this out later on, but for now it's just a closed interval. Okay. Closed interval to reals, anything. And f is continuous. So we need the continuity. We shall see continuous. All right. I'll quickly review the definition of continuity in this just okay. So here, remember, we need it to be continuous on the entire interval a comma b. We could have taken 0, 1. I'm taking a comma b. Something like this maybe. What is the sense of it being continuous? Basically, the point is that if you want to make small changes, so this is very careful statement, okay? If you want to make small changes in the range, you can do it by making small enough changes in the domain. Okay, what does it mean? It means, again, just quickly reviewing the definition, okay? So remember, I'm not saying that, yeah, that's the same thing as saying that if you make small changes in the domain, then you make small changes in the range. But I'm saying it more precisely, that if you want to make certain small amount of change in the range, you can do it by making small enough changes in the domain. So let's say this is x naught, and let's say the amount of change you want to make is by some epsilon band, epsilon amount of error, whatever you want to call it. Okay. So I will just quickly do the definition. This is not a part of the class to do the definition today, but still, and we won't need a very precise definition anyways, but still. Then the idea is that you can take a small enough. So given what I'm trying to say is that given epsilon greater than 0, you can find a delta such that for all x such that x minus x naught is less than delta, meaning that if you make this amount of change in the domain, it will imply that you would have succeeded in making that amount of change in the range. We shall not need this too much though, okay? But just to know the definition. Now this is what it means for it to be continuous at a point. But really what we are looking at is that we want continuity in the entire interval, and that really is very different. That's why it's called one of the global properties. Okay. So what is the first statement with this condition? F has, or I should say F is bounded. F is bounded. This is not the extreme value theorem. It's a weaker version of that. Okay. Let me, we'll explain that. F is bounded. What do I mean? I just mean that there is a M and a M, small m and capital M, such that this is what happens for all x in a comma b. This happens for all x in a comma b. Okay, this is one part of the extreme value theorem. Okay, before we move forward maybe into proving this and then proving the precise version of it, let's think of a function. Any questions? Let's think of a function which does not have this property. Okay, so what I'm saying is if we remove the continuous condition, Can you give a counter example? I've only removed the continuity condition, not any other condition. No. Function which is not continuous but is bounded. So you see, I've removed the continue. Okay, so I should say precisely, I've removed the continuous condition. Okay, and f is bounded. No, not bounded. Yeah. So you want to give a counter example, which means a function f on a comma b, which is not bounded. Maybe that's what you said. I'm sorry. Yeah. Example of f on a comma b not bounded. It really helps to do these examples. You will see later. It really helps you to think about these things. Right? So what I'm looking for is an example of a function on the closed interval a comma b such that it is not bounded. Not bounded means that, of course, the image set is not bounded, means that you can't write the image in like this between two numbers. You have to be more precise. If you say tan x, what is the domain and what is the range? Between? But that's not correct. Think about why your example is not correct. No, 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 no. So listen. Of course, you can never give me an example which is continuous, because otherwise the theorem will not be true. We said that if it's continuous, it will be bounded. So of course, any example you are going to give me will not be continuous. But the problem with your example is something else. I want someone, maybe can try to spot it. Open or closed? If it's open, then it also doesn't answer my question, though it's a good this is a good thing, but it doesn't answer my question because I need a closed interval. I need a closed interval. So Raghav, your mistake was that your function was not defined in the interval you had defined it in. You see, my function doesn't have to be continuous, but it has to be defined. When I say the range is R and the domain is this, it means I have to be defined. If you say 0 to pi, I mean, these are silly small things, but you know what I'm saying? It's not defined at pi by 2. So you can't include pi by 2 if you keep the usual definition. So we have attempted to change it to this, but this also is not complete because it's not closed. So can anybody make this closed? I mean, this is a good example. It's just that some technical details have to be worked. I mean, simple technical details. Yes, it can. You see, it should be able to be constructed. Otherwise, otherwise you would have heard that extreme value theorem implies continuity. Think about it. Right? I mean, I'm saying, okay, when you say can it be constructed, yes, it can be constructed, and it also exists. Sometimes it happens that it exists, but it cannot be constructed. But in this case, it exists and can be constructed also, if that's what you meant. Yeah, I mean, it certainly should exist. Otherwise, being bounded would imply continuity, Lord. But that's not true. Right? Obviously, not true. Okay, but it's obvious, but we are not able to find an example yet. That's a different thing. I mean, you guys are very close, but I think it's because it's a little unfamiliar here how to extend it. It's very simple. My hint is that it's very simple to extend it. Extend to, I mean, we don't even need minus pi by 2. We can just keep from closed so that we don't have to take that headache of the other side. Sorry, my voice is yeah, 0 to pi by 2. We want to extend, we just want to extend at, define it at pi by 2. At x equal to pi by 2. Yeah, you can define it anything. That's right. Because your job is done, right? Your job is already done. What you wanted the unboundedness, that's already done. Why do we care now? Right? Why do we care? We can define it to be anything. That is again very silly, but sometimes these things don't strike us because we don't do these extension questions and so on so much. So, anyways, but it's very simple. Yeah, simple like this. You see, what is really going wrong is that the function is going to basically is unbounded means it has to go to infinity at some point. Okay, and these functions. So the point of all this is that if a function doesn't have the boundedness property, then the type of discontinuity it will have will be non-removable. You cannot. This is a hopeless function. Okay, you cannot make it correct now. Okay, it's a good example. Right. Now, what is the sense in which this theorem is true before moving on to other angles of examples and counterexamples and then to a proof maybe and then to applications? What is the sense in this which is true? So the idea is that, look, continuous functions, this is the one way people should start thinking about these things. Continuous functions are functions which do not change too many properties of the domain. A continuous function, or rather any function, we think of functions as things that take input and give output. That's one way we think about it. But you can also think of functions as something that, like this function, as taking a line and then bending it and so on. Don't think of it on the input level. Think of it as one malleable whatever thing and then, bending it or renaming the points or some action happening on it and changing its shape or whatever. That kind of thing. Okay. The idea is that continuous functions do not change the input set too much. This input set is bounded. Okay, closed a comma b is bounded, but it is not just bounded. Okay, it is not just bounded. So the sense in which I want to say it is not just bounded is the following. This is small. It is obviously bounded. Even open a comma b is bounded, but it is small. What do I mean? In what sense am I saying it is small? I mean that, look, if first of all, it has a maxima and minima. In that sense, it is small. Okay, but more a little thinking about it in a little different way is that if you take any sequence in this, okay, just if you take a sequence in this set, let's take a monotonic sequence. Monotonic sequences are enough to consider for reasons that, because every sequence has a monotonic subsequence. So maybe all of us have not done it, but let's just consider monotonic sequences for the time being. If you consider any monotonic sequence inside this set, okay, it's limit means it's the place where it goes finally may not be b, it might be some number, but it will be inside the set, right? So if you take a sequence, basically if you apply an infinite process again and again and again, then the eventual place where that goes is still inside this set. Okay, it has its boundary points. Okay, basically any limit point, any sequence, its limit will be again inside this set. That's why it is what is known as a closed set. We will not need the definition here, not need the definition, but I'm just saying, and more importantly, why I'm trying to say this is that these things will give you intuition in the sense that this is not small. Open A comma B is analytically speaking, geometrically speaking, big. It is big. Why? Because if you're inside this, you cannot see the endpoints. Think about it like that. That's the way I like say it. If you're inside this, you cannot see the endpoints. And you can think about it in different ways. Like, you take a sequence going to B, it doesn't, its limit is not there in it. It doesn't have a sink, it doesn't have a boundary. So that's big. So that's why closed, these intervals are different. And so because continuous functions have this property that they take these small sets to small sets, so they're taking this bounded set to a bounded set. That is the idea. And it is not just this. Continuous functions preserve a lot of good things. Okay. Meaning that if you have a set, if you have a, if you define a continuous function, let's say on in something like this interval, open interval, then its image would also be an interval, open or close, but it will be an interval. That's an intermediate value property, right? The image also attains all the values in between, because this is a set which has all the values in between. So it doesn't change the nature of the set. And that's a real essence in which we want to think things about later on. We want to not think things in terms of points, it takes this point to that point. No, we want to see what it does to the shapes and to the sets that we are interested in. In fact, that's how continuous functions are defined later on, but we'll not say about that right now. But what I've said till now, that this open one is big and so on, actually, if anyone has questions, okay, actually this can lead us to ask a very interesting question. What if I take a continuous function on an open interval? Will it be bounded? And the answer is no. I mean, you people have already given me the answer, right? The answer is no. I mean, minus pi by 2 to pi by 2 tan. So this does not imply bounded. Does not imply bounded, right? Let's try to see why this happens. This will actually now help us to do the proof. Okay. This almost will give the proof in just non-formal way. If you're taking, let's say from 0 to pi by 2. So I'm drawing them on different places. Is that a good idea? No, that's not a good idea. We don't need that here. Why? Like, what is the essence of it? How does it escape to infinity even though the domain is finite? Of course, you can say it increases faster and faster, but that's a much more advanced concept. That's a much more secondary concept than what we'll see. How is the tan graph? Something like this, right? Whatever, something like this. No, it can't be like that, but whatever, something like this. Yeah, it's convex for some time. Yeah, the point is that this is how it is. Okay. See, the idea is that when you tend, you go from half. No, I'll have a tough time with the numbers there, so I'll just take like this: x0, take the image, x1, take the image, x2, take the image. These things that are going towards pi by 2, this sequence, okay, it's going towards pi by 2. The images are not checked by anything because the sequence itself is not checked. The limit checks it, but there's no limit to this in the set. So the sequence keeps going. In some sense, it goes to infinity. It's going to open pi by 2, but in some sense, it's going to infinity because it doesn't have an endpoint. Right? And so the image values tend to escape. If there was something to check it, let's say if the function was defined at pi by 2, right, then the pi by 2 would check it, right? That pi by 2 would will check the images, all these images. It will check, okay, you have to stop there or something like that, or you have to tend to this image or something like that, and it will be bounded. This is the essence in which it fails. So this brings us to another definition of continuity, which I have covered in the past, and maybe some people might be knowing. I'll state it, and um, then I'll be using that to prove this result. I think that will be well, it doesn't really matter. Yeah, but let's use that definition because there's certain flavor in that which I like, and it's kind of will be useful. So see, more than anything, what are we seeing? That, well, the set on which your continuous function is defined, that set must have the following property. Number one, it must be bounded. Of course, continuous. So at this point, I'm just delaying the proof just one more minute, trying to say that, trying to abstract, because what properties are we using about this closed interval? And in fact, we are using all, because that really defines closed intervals in some sense. It defines closed intervals. Okay. So I must say like proper A, like this A must be bounded. That's obvious. I mean, if it's not bounded, then obviously there is no chance. And number two, any sequence in A must have its limit in A. In the most naive sense, A must have all its limit points is one way to say it. But any sequence in A, if it has a limit, just think, for those who have not done limit points, just think limits. Any sequence in A which has a limit, assume it has a limit in A, has its limit. This is not enough. Has its limit is not enough. That will just be completeness. Okay. No, that will not just be completeness. I'll take that back. Has its limit in A is what I'm trying to say. In A, that's all. Yeah, has its limit actually doesn't mean anything. Yeah, because the space could be in A on its own. Has its limit in A. That's the type of set it should be, and the closed interval 0, A is that type of set. And I believe what you people can imagine is a union of two closed intervals would have that property. It would be difficult for people to imagine maybe other sets which might have this property. So I'm not discussing them right now. Okay. But there are very interesting sets which have that property. Okay. This would imply that continuous functions are bounded. Is bounded. So you see, by spending some time trying to understand the idea of this and what this means and what this does not mean also, because it means when does it not imply continuity and so on, actually helps us to abstract this. But this is so powerful, in fact, that like this, if A, this F, if all continuous functions from A to if F, this and F continuous imply F bounded, separate statement. If this happens, so if A is a set, okay, if A is a set, you can assume it's like a closed interval maybe, but right now it's just a set. And what I'm saying is that some of its properties, a property of that set based on the functions on that set. That's really another way we want to understand mathematics in general. You want to understand a set not through its elements, but through some set theoretic properties or functions defined on that set. Now, really, functions defined on that set are the really interesting way to understand sets. Like when you have finite set 1 to n, you do permutations on that and try to understand that set, structure, partitions, a lot of other things, right? In general, when you want to understand any complicated thing, you want to move it around, right? You want to move it around, you want to apply symmetries on it, or you want to apply numbers to places in that set. And then only you can understand, right? You put it in different situations and you try to understand it. So basically, we're trying to understand the set A through functions defined on that set. So in that light, I'm making this statement that if A is a set such that all continuous functions on that set are bounded, then A is closed set. Then A is a closed interval in some sense you can imagine, or A is a closed set, or A has properties 1 and 2. This is a, it means that like this properties are very strong. Okay? They actually will define the set for you. So in some sense, these are universal properties. Okay. But anyways, these things you can try to show later on. Okay. But it will be difficult because they are not just closed sets, and so we'll have to go prove the properties A and B, which you can do. But for the time being, and these kind of statements are true throughout, even for IVT and so on. But anyways, I hope that is fine. Let's actually come to the proof. Yes. Closedness, yeah. Like you can see, I mean, see, first of all, you saw that this is essential in the proof. It will be essential in the proof that you saw, right? And that's what I'm saying. And these two are enough for the proof. So I'm saying that any set that has these two properties would work. Would have this, would imply that a continuous function on that set would be bounded. Not just closed interval 0, comma 1 or closed interval. Yeah. Mm-hmm. 1 by n square doesn't converge to pi square by 6. No, no. Yeah, some of that will converge to pi square by 6. But the sum is not there in the set. Sum is not there in the set, right? If you take some partial sums after 100, I mean, no 100, just take the second term. First S2, I mean, first term, it will not be. No, any sequence in that will have its limit in that. Right? Yes, just after the second step. Yeah. Anyway, so we will prove this. So it's very easy to prove boundedness. How do we prove it? Now let's come to the proof. We want to show that f is bounded. So statement is clear, right? F is continuous on a closed, just take closed interval a comma b. F is continuous and we want to show it's bounded. Okay, by the way, I must just state one property of continuity. Okay, so F is continuous also means, and this is very easy, that if these things tend to X, then the images will tend to f of X. Basically, I mean, as you're going close to X, the images are going close to fx. This is actually can be taken as definition of continuity. This is the definition I'll be using. I didn't say that. Got lost in all this. Okay. This is the definition we'll be using. I mean, if we don't really see, the point is that we can never give a direct proof of this. I don't think so. Because, see, the point what I'm trying to make is that M cannot be constructed. That M cannot be constructed. You cannot tell me what that M is in terms of what I've given. You can only prove that there exists such an M. Is this meta point okay? Because the general state, Yeah, my point is that the function f is general. You want to prove this statement for general functions, general continuous functions. Now, given a function f, you can't find the m in terms of f, like 2 times f or something like that. It's not possible. Or function containing f, a, and b. With these three information, you cannot construct the m. It's not possible to construct the m. We can only show that the m exists. So whenever you realize that this is going to have, this is what the situation is. In this case, it's that clearly what it is. You cannot construct the m, which means you cannot give a constructive proof of this. Which means you have to only show that it exists. And on constructive proofs, even these words would be enough in most cases to tell you that by all means, it seems like we'll have to do a proof by contradiction. Okay. Non-constructive proof means you cannot construct it. So you can only show that it is not true that such an m does not exist. You can only show that. Right? It is not true that such an m does not exist. And that means that's what contradiction means. Right? You assume that an m does not exist and you show that it is wrong. Right? This is, I mean, these are the, this is very, because maybe it's obvious to people that they'll go by proof by contradiction, but I'm just giving in general how do mathematicians general come up with this and so on. And basically these kind of things later on you'll be like showing, okay, this theorem, this big theorem can never have a proof by contradiction, or they can never have proof in ZFC or in ZC or blah blah, like so on that axiomatic level and so on. But this is just on a strategic level. I don't know the axiomatic level myself too well, but point is on a strategic level, it's clear we have to do a proof by contradiction. Now, of course, you may see a general statement like compact set, image compact set, and you may see, look, there's no proof by contradiction here. But the point is that if you dig into that compactness statement and all, somewhere there will be a negation, double negation used somewhere. Okay, but my point is that it's not constructive, it's existential. So we will assume it's just a general picture of when you can smell a proof by contradiction. Like it's maths has this meta patterns running through it. Okay, so assume that f is, so we'll just do the upper boundedness. Lower boundedness is same. I'll do the upper boundedness because then we will generalize this. I was thinking of this. We'll generalize this to some other kinds of functions which are not continuous, but they're, we'll see. Assume that f is unbounded. Okay, f is unbounded. What does it mean? How do you write it out? How do you write this? This means that, I mean, you can take x1 such that f of x1 is bigger than 1, x2 f of x2 is bigger than 2, and so on, right? This is just the easiest, and it's a complete way, like we're not missing anything, way of writing unboundedness. So remember, unboundedness is a loose concept. You can always play around with it a lot. There's so much room in that. It's more of a, I must say, it's more of a qualitative property than anything. As it's, you can play around with the numerical aspect of it when needed, because it's in some sense not a numerical property, especially in these general cases, because we're not actually asking for the bound. And these are the things that people usually don't get on a deeper level at, and so the proofs become a little more like, no, but here boundedness is a qualitative property because we are not constructing it. So we can play around with this and we can write this. What do we get next? Like, what should we do next? So we assume that it's unbounded, right? So this is what's happening. But I have already said that these x1, x2, and so on are in a comma b. So how can you use that? As sorry. Mm-hmm. No, I don't understand your argument. Let me think what you said. No, no. The just the boundedness will not be, just the boundedness of the interval will not be enough. That way you can say that, that way you can prove this result for open a comma b also, right? You can say b plus 1 is an upper bound, if that was the argument. But the point is there are sinks. See, the real numbers are quite strange things, right? There are sinks everywhere. So what you can do is simply you can take the limit of the sequence. Now the sequence may not be have a limit. People who know analysis might say that this may not be have a limit. Then what will you do? Point is that there will be a subsequence of this which will have a limit, right? There will be a monotonic subsequence of this, and that will have a limit. It will have a supremum, right? It will have a least upper bound. That will be the limit. I mean, you don't even need to get into that actually. You can actually choose this so that it is increasing. You can actually choose. That's why I'm saying we can always do all this. Whether in the exam, you don't want to state such a strange result. So you can choose, I guess. You can choose x1, x2. No. Yeah, you can do it, right? You can choose them so that they are increasing. You see my point? You can do this. Why? Because you take an exponent bigger than 1. Now, after that point, there also must be a point where, I mean, x2. Oh, no. You cannot. You cannot. You cannot choose that it is increasing, right? Because, sorry, yeah, that I was just trying to cut that, but you cannot do it in the function. You have to do it with the real numbers. Yeah, a comma b. You take an x1. It's, well, let's say 10 bigger than 1. Now you cannot actually say that in this part only I can choose my let's say x100. No, you may not actually. It may be unbounded here. You don't know. That's what you're trying to prove. Though it's an obvious statement, but they're trying to prove it. So you cannot actually. Right? You cannot. You cannot choose it to be increasing here. So you have to take an increasing part of it. You take an increasing subsequence of it. So that is something which you'll have to assume then. I will not prove it today. I mean, we have, yeah. You take an increasing, yeah. Oh, that's right. Um, but you may not be able to find such a place, right? You don't know how to find such a thing. It may be locally non-monotonic or some things like that. It may never be monotonic anywhere. No, you cannot do that. Those are the hard I mean, it's not even true. You have infinitely wiggling function because these are not differentiable functions, and even differentiable functions which are not whose derivative is not continuous, but they don't have these properties. So yeah, those things we want to happen, but then those are more secondary than what we are doing actually. So, and they don't even happen. So yeah. So anyways, you can assume that this is increasing. You can take a part of it, subsequence of it, which is increasing. So you can assume this is increasing. Now, because this is increasing, it will have a supremum, right? And we know that its supremum really cannot escape 0, comma 1. It's quite clear. Right? If you take the least upper bound of this, it has to be inside a comma b. And that x will be the x naught, I should say, not x naught, maybe t, maybe, or L is the limit, right? So this will be L, and that's my point. Right? You can now, it's easy. You can take the function on this. You can take it inside. It has to be FL. Yeah, think about it. So this sequence limit must be FL. Now FL has to be a number because the range is reals. So this limit has to be a number, which is not possible, right? Because this is xi is bigger than I. F of xi is bigger than I. So that's the contradiction. And so it is not true that f is not bounded. And so we must agree that it is bounded. Right. And there are several proofs of this. This is where I've used the sequence properties. Now, sequence property you will not be able to use if the rationals were not a dense set of R. That's really the essence of being able to use sequence properties. Because real numbers are uncountable, they are big and such, but then they have a dense set, which means the rationals are ever present in the reals in some sense, right? That's the reason why sequences are being useful. Okay, but in fact, this is not. We don't have to use this. There are better proofs which I'm not giving because we don't want to complicate the situation. Okay, but what we can say even at this level of abstraction is that all we needed is that any sequence, its supremum is in the set, its limit is in the set, and that it is bounded in itself. That bounded in itself, well, that actually, I'm sorry, I mean, the bounded actually, this actually implies the boundedness, right? But still, I mean, we are not doing some minimal model program. We are just doing it, so it's fine. Okay, so this is what it is. This is a proof of the statement. Now, there are other proofs. There are inductive proofs. You can do some sort of induction on this thing and do. Interestingly enough, but I don't want to keep the balance here, so I don't want to go into that right now. Yeah, so what was my plan to do? What was my plan to do next? Now, we must do some applications, but I wanted to do an abstract, another this thing of it. There are let me state it. If I keep saying, then it will not finish. Let me state that. So yeah, we look at, see, we generalize continuous functions in several ways, right? Generalize continuous functions. So what is one way maybe which you can generalize? Maybe you could look at those functions f. Okay, you can look at a function f such that limit of x tending to a from the left side is f of a for all a. You could look at these type of functions, right? These are these are not necessarily continuous functions. They are those functions which are continuous left continuous functions. Examples of left continuous functions, greatest integer function maybe, right? Greatest integer function would be a good example. Other examples are the right continuous functions and so on. So what you can one second. So does a function being left continuous imply, and of course on a bounded interval, does this imply boundedness? And of course f is defined on a open interval, sorry, closed interval, not open. You can think about this. Think about this. I'm not going to do this. This will have I think should have a straightforward answer. But what I was thinking is of a more general, of a more intrinsic this thing. So there are functions of this sort. So let me save that. So let's you have a function from a comma b of the following kind. For any epsilon, so you take any point in the image set. For any epsilon, okay, this kind of thing, you can find delta such that this entire thing, is less is less than f of c naught plus delta, f of c naught plus epsilon, meaning that you can always tame the function on above, from above, I mean, so you can always control the positive errors. You can always control the positive errors. This is not left continuous. This is very different. Left continuous thing you can think about later. Okay, that should be a very easy answer, I believe. You can look at these type of functions. These are not necessarily, yeah, these are not necessarily continuous, of course, but I am thinking of a counterexample. Anyways, yeah, this thing, right? So given epsilon greater than 0, there exists a delta. I'm just writing the definition of this. Okay, there is delta such that if x minus x naught, if x minus c naught is less than delta, it implies that f of x less than this. So as I was saying, you can control the positive errors, but you can't control the negative errors. Can't control the negative errors. Okay, and these functions are called upper semi-continuous. Now these are very important functions in descriptive set theory and things like that. Okay. But not that I know, I just know a few theorems. Okay, upper semi-continuous. Why? Because I mean, you can think about it, right? It's that you can. I mean, the word I'm using is, this is where I like to think about it. Positive error can be controlled. Otherwise, you'll forget this definition after some time. This is what I thought of trying to explain it. So maybe it was there in my mind, but I had never conceptualized it. That's the good thing about teaching. So positive errors can be controlled. So this is the definition. Okay. Now, as you people might already feel, right, that on a closed interval, these functions should be bounded above at least, right? On closed a comma b, closed a comma b, f is bounded above. I mean, this type of f. Okay. Upper left semi-continuous. Yeah. Wait a minute. Why did I say left? No, forget about left. Just remember upper semi-continuous. It's also said right semi-continuous. That again you can understand. Upper, I like upper better here. Right would be confusing. Okay. Now you can understand. I mean, these are like these continuous these functions kind of tend to continuous functions. Those are actually proper concepts in terms of intersections and such. But yeah, we want to show this. Let's show this. This is like a good exercise to apply the concept there in this problem. There are better definitions of this upper thing, but I'm not giving it right now. Let's prove this thing, then we can state it. So most of the proof should be similar, I believe. Let's think about it. So on a comma b, f will be bounded above. Again, you may feel that it looks correct, right? So I'll leave the usual proof, sequential proof for homework. Try to prove it, but I'll do a different proof maybe now. That is a different type of idea. That idea can be used to avoid the sequential things in most places, I believe. Yeah, where it's non-sequentially also true. Yeah. Okay, so sequential proof homework. You can try it for homework. Same proof as I've given there. You can try to mimic the same proof. We'll discuss it in next later class if needed. Slightly different proof I'll do. That proof surely will work. Okay, but we'll do a different proof. So we want to use some kind of an inductive argument, inductive nature argument. We want to show that f is bounded on all of a comma, on all of a comma b, right? So my question to people is that can you find me, find or can I can't really find. That is where it's loose terms, English words can, yeah. Can we show that there exists x naught, sorry, such that f is bounded above on a comma x naught? So my question is, can we get started? Can we get started? That is, or rather, this will not actually get you started, I think. This will get you started. Closed. So I'm saying that, okay, maybe we cannot prove it for a comma b. Fine. Can you at least find some x naught? Can you prove it for a smaller interval? Smaller initial interval. Now, this word initial interval makes sense here, and this is general in the theory of well-ordered set. It's not a well-ordered situation, but still sets where this initial intervals and those things are ordinal numbers is like when you put order on cardinals, well-ordered cardinals, so on, is you are used, and a lot of things are done with these words because they're more important because we don't have pictures. Here you at least have pictures. There you only have good choice of words that can save you. I mean that's what I felt studying. Yeah. So try to use the local this thing. So you can prove this, right? You can prove it by local, I mean, just using the definition of semi-continuity in this case, whatever is given, isn't it? Because I mean, you have f of a, you have f of a, and you can basically bound. You can find a bound. Actually, you can find a small enough bound around f of a as you want. Small, you can. The upper bound will be more or less f of a, not f of a, but as small, close to f of a. Point is that you can take a, I mean, you can take an epsilon, right? You can find your delta. I'm doing closed interval, you can do delta by 2 and all, and you can do closed interval, right? So this entire thing, see, that's what my point was. Bounded above, bounded below, we cannot say. Bounded above, we can say, right? We can say that f of um, t, yeah, is less than f of a plus epsilon for all t in a comma delta, right? That delta is your x naught, upper bounded. So this precisely, right, upper bounded condition. Leave this here. So my point is that we can get started. There is an x naught for which this works. Now, in some sense, what we will do is we will find the biggest of these x naughts. Of course, we cannot say biggest, but we can say supremum, least upper bound, which we have assumed exists. That's something which we are not proving, at least in this sequence. So we can take this because really we want to show that the maximum of these x naughts is b. That's what deep down we know is true, and that's what we want to show. So we want to use that as a leverage for our constructions, because once you have the things properly written, math itself does the work for you sometimes. So I'm defining a set as x such that f is, or the property p I can say is true, blah blah blah. F is bounded above in, of course, with different bounds. The bounds will change. Okay, so okay, now this was the set A. So construction of these sets, right? Because really maths is, because what happens is the machinery we develop is smarter than us sometimes. The set theory and also which we understand, but they are smarter than us, and that's why we develop them so that we can don't have to always think everything at once. So my point was that once you write these things, and set theory and all the supreme uniform properties start to take action on their own. So this method of constructing these sets are quite, these are not ad hoc. These are general constructions, okay? Because the goal is you want to show that B is the biggest of subset. So this is like extremal principle, right? What you want to show has been converted to an extremal problem, and you're taking the big, trying to show that it occurs at the boundary point of a set. And most interesting things happen at this kind of things. Okay? So yeah, that's the point. And F is bounded above on sorry f is bounded above on a comma x is what you want to, I mean, sorry, you want to show that the supremum of a supremum of this set um, um, is b, and you want to also show that the supremum of this set is b, and it's also in the set. Those kind of things you want to show. Why did I show that x this is true? Because I wanted to show that a is unbounded. I wanted to show that a is unbounded. That was my point. Okay. What did I say? No. I wanted to show that a is non-empty, right? Because if x naught was not there, then a would be non-empty, and if a might be empty. Now, if a is empty, then we can't use all this, because we will soon say. So let me not write this for. We will say let let K be sup A. Now I cannot really write this if A was empty, because what is the least upper bound for an empty set? If the set is empty, anything is an upper bound, and so the least of it will be minus infinity, and that's bizarre and so on. So like we want to first show non-empty. That's why you would say non-emptiness is a general step in the proofs, this kind of proofs. So that's the first thing. That's the first thing. So this is a supremum. Now you want to show that the supremum exists, and because these numbers, all these x's that you have are again inside the closed interval, so the supremum would also be inside the closed interval, right? So supremum will be in the closed interval a comma b. So here we are just using, this is a more fundamental proof. We're just using the fact that supremum exists in this interval itself. Supremum exists, that's true because it exists in reals. With this interval itself, we are not using the combinatorial thing. We're not using that every sequence has a monotonic subsequence. Okay. That's the point. So supremum is there. Now you want to show that the supremum is B. Now I'll leave the proof, this part of the proof. Okay, you try to show it. So you assume if the supremum is not B, if the supremum is not B, let's say the supremum is K and the K is not B but somewhere here. I mean, it's easy then, because I mean, for this part you have a bound. For this part you have a bound, right? Let's say the bound is M. Now around K again you can make an interval. That's just the incremental thing. Around K you can make an interval, and again you can bound it around Fk, upper bounded by around Fk. So you can, if K was not B, then you can find a bigger element. So if K is not B and you are, then it's not a upper bound, you are able to find bigger things. What I mean is that K, if K is supremum, if K is not B, then you can find K plus delta such that it's bounded on A plus A plus K plus delta, K plus delta. It's bounded on a bigger thing because you can take the bound on this part and this part and you can add the bounds. That's the thing about finite numbers, right? If you add two of them, then that's the part we are using here. Still finite. I mean, that's the abstraction of the boundedness there. So it will work on any kind of thing which is closed under addition. But that will be on top of that meta thing. Then the functions would not be from f but from r to, from something to r, but on some different set. We don't really want to change the range right now. That will be right. So then you have found a bigger one. So the k has to be b. That proves the k has to be b, and they're done. And the k, the supremum of the set has to be b. Right? Yeah, I guess. Let me just go through it again 1 second. So there might be a little problem here. Yeah, because I've said it, K is the supremum. That's the problem. Yeah. K is the supremum of this set. So I cannot, yeah, anyone is saying something? Okay, yeah. All right. K is the supremum of this set. So it doesn't mean that it will be bounded. The point problem is this, see. When you say K is the supremum of this set, you cannot say that F is bounded above. I mean, K may not be in the set. K is not in A. So we cannot say that A is bounded in closed A comma K. We cannot say that. But what we can say is that A is bounded in open A comma K. That you can prove. That you can prove. Now, how you can prove that is easy. I mean, because I mean, if there was basically anything less than K, if you take anything less than K, then A to that thing will be bounded. So if K1 is less than K, then K1 is in A. I mean, not K1, but something bigger than K1, because it's the least upper bound. If you take something less than, then that's not an upper bound. Then there is a K2 such that A is bounded, such that F is bounded from A to K2, right? Because it's the least upper bound. If we take anything less than that, that's not an upper bound. which means that something is in the set which is bigger than that thing. This K2 is there in the set, which means it's bounded on A to K2. So the point is that anything less than that you take, function is bounded on that. Okay. So the function is bounded on this, I guess. And now you can use the same increasing argument that I gave, and you can do the problem. I mean, you will be able to increase it because it's not equal to B, and because it's the property of a locally used. And so it will be done, right? So that's the proof. Okay. There are more things to be said here. These actually will imply the extreme value theorem. We didn't actually prove it. We just proved that it's bounded. Continuous functions are bounded. The existence of the maximum we have not proved yet in our class at all today. We'll do it, and then maybe we'll see some applications, and we'll see connections of this with the intermediate value theorem, because that's really where it comes useful. Otherwise, on its own, it's not very useful. Okay. So yeah, we shall continue that the next time. Tomorrow I'll take some other classes, not this class. I'll tell you